This question is from GATE 2014, Mechanical Engineering Paper Set 3, question number 38. A slider crank mechanism with crank radius 60 mm and connecting rod length 240 mm is shown in the figure. The crank is rotating with a uniform speed of 10 radian per second counterclockwise. This is how the crank is rotating with 10 radian per second speed. For the given configuration, the speed in meter per second of the slider is, we need to find out the speed of the slider in meter per second, which is nothing but the translational speed. It can move either towards the right or to the left. So either way, we need to find out the speed of it. Let's see how this will be done. For this, we will assume that slider and crank are both falling in the same line. Let's name this point as A, this one as B, and this point as C. We have a triangle ABC, which is a right angle triangle because this is 90 degree. We can easily find out this angle at which the connecting rod is inclined. Let this angle be theta 1. Now we are being given the angular speed of crank rod, that is nothing but omega AB, which is equal to 10 radian per second. We can find out the translational velocity of point B using this speed. So we'll have it here, translational velocity of point B, which is tangent to the path of crank radius, circular path of crank radius. We can find out as VB equal to angular velocity omega AB into the radius of crank, which is 60 millimeters. So it can be 60 into 10 to the power minus 3 meter. So this becomes 10 into 0.06, which is nothing but 0.6 meter per second. Now that we have VB, this can help us to find out the angular velocity of connecting rod. As the crank radius rotates counterclockwise, the connecting rod will also rotate counterclockwise because point B is shifting towards left, and therefore correct direction of velocity at B will also be towards the left. This will be VB. This point being falling on both the rods, connecting rod will also be shifted towards the left, that is, it will rotate counterclockwise. We can find out angular velocity of this connecting rod, which is omega BC, by locating the instantaneous center of this rod. So to locate instantaneous center of the rod, we'll extend this and then connect it to the perpendicular to C. Drawing perpendiculars from both the point where they'll meet will be the instantaneous center. This is a right angle. This is also a right angle. So this point is the instantaneous center. So we can find out omega BC by doing translational velocity of point B divided by the distance BI. It is also equal to translational velocity of point C. Now as the crank rod rotates counterclockwise, it drags the slider towards the left. So VC, translational velocity of point C divided by CI. This is the relationship we can use to first find out omega BC, and then using omega BC we can go ahead to find out VC. Let's do it. First, using this, we have omega BC will be equal to VB we found out here 0.6. We need to find out the distance BI. So to find BI, we will use this right angle triangle IBC, which is right angled at B, and name this angle to be theta 2. So first, to find this distance, we'll need theta 2. Now to find theta 2, first we'll need theta 1 because theta 2 is nothing but 90 minus theta 1. So let's find out theta 1. We have in triangle ABC, tan theta 1 will be opposite upon the adjacent side. So we have tan theta 1 is equal to 60 by 240, which is nothing but 1 by 4. Tan inverse of 1 by 4 will give us theta 1, which is 14.036 degree. We know theta 1. From here we can calculate theta 2. Theta 2 will be 90 minus 14.036, which comes out to be 75.96 degree. We have theta 2 as 75.96 degrees. Now in this bigger triangle, we have one side BC. Using this side and this angle, we can use the trigonometric relationship and find out the distance BI. Let's do it. So distance BI upon BC defines the ratio tan theta 2, trigonometric ratio tan theta 2, because BI will be the opposite side to theta 2 and BC will be the adjacent side. Therefore, BI will be simply given as tan theta 2 into BC. Let's substitute. We have tan of 75.96 into 240. It's in millimeters. So we'll get BI in millimeters as 960 millimeter. Of course, in the figure also we can see that BI is very long compared to AB or BC. So this comes out to be 960 millimeters. We can also find CI just in continuation to this. Either you can use Pythagoras theorem or you can use the same trigonometric ratio. So if we use Pythagoras theorem, we will have CI will be equal to under root of, CI is the hypotenuse side, so it is 960 square plus 240 square. Calculating this in the digital calculator, we have CI is 989.54 millimeters. From here, we can find out both omega BC and then find out VP. So first thing, omega BC will be 0.6 upon 960 millimeters, which is nothing but 960 into 10 to the power minus 3 meter. This comes out to be 0.625 radian per second. And using this, we can find out VC finally. VC will be equal to 0.625 into 989.54 into 10 to the power minus. This gives us the answer in meter per second as 0.618 meter per second. So finally we have the velocity of slider, which will slide towards the left, as 0.618 meter per second. Let's go back and fill in the answer. For the configuration, the speed in meter per second of the slider is 0.618. To learn more about slider crank mechanism, you can refer to the NPTEL video Module 4 Lecture 1 Balancing of Single Slider Machines. It is from the course Lecture Series on Dynamics of Machines. This course is by Professor Amitabh Ghosh. He is from Department of Mechanical Engineering of IIT Kanpur. I hope this solution will help you clear your doubt. Thank you.